Imagine that you had a sphere, and all over the surface of the sphere was a distributed charge. Now imagine that sphere spinning. The charge on the surface of the sphere moves with the sphere. This is basically creating a bunch of currents going all around a single point, the center of the sphere, which would basically create a magnetic field. So what we can treat this as is a charged object that's spinning creates a magnetic field. All right, now let's put quantum mechanics into this. See, an electron is a charged object, and an electron has spin. Now, it's not moving, but it still is spinning, but not spinning. Quantum mechanics is weird. But anyway, the result of this is that electrons have an inherent magnetic field to them. Now, the formula for the magnetic dipole produced by the electron, and the magnetic field depends on the dipole and how far away you are. But the formula for the dipole of an electron is given by this formula right here. This is the magnetic dipole of the electron. This E is the elementary charge, that's the charge of an electron. H is a quantity known as Planck's constant, which is this. And Me is the mass of an electron. Now we have two other numbers here. M is called the spin number of the electron, and L is called the orbital orientation number. Now every electron has a spin, even electrons that are free that are unbound to an atom. And that spin quantum number is either going to be plus 1/2 or minus 1/2. One thing about quantum mechanics is that these numbers are quantized. They are certain specific values. L, on the other hand, that depends on the electron's orbit. And the possible values of L depends on which orbital shell it's in. If that electron is in an S shell, then L is automatically 0. If it's a P shell, it can either be 0 or plus or minus 1, etc. What do these numbers represent? Well, M, the electron has this inherent property spin that is unrelated to it actually spinning, but it has an inherent property of the electron. L is the amount of angular momentum that is in a particular direction. Now that doesn't mean we pick this direction, the angular momentum is in that direction, but other directions have their own angular momentum. No, quantum mechanics is not that easy. There are two numbers associated with angular momentum for an electron's orbit. One number says how much angular momentum there is total, and that will tell you which of these shells you're in. S is 0, P is 1, D is 2, F is 3. L tells you how much of that angular momentum can be ascribed to a particular direction. The rest of the angular momentum is just there, directionless. So those two terms combine to create the total magnetic dipole of a particular electron. Now, you can have protons have a magnetic field, and protons' magnetic field would have a similar formula. You'd have different numbers because protons in an atom are slightly different than electrons in an atom. But more importantly, instead of Me, you would use the mass of a proton. A proton is 2,000 times the mass of an electron. So even though protons do have magnetic fields, and for that matter, neutrons create very, very, very tiny magnetic fields, the magnetic fields they produce are completely overwhelmed by the magnetic field of the electron. Now, another thing about quantum mechanics is that no two electrons in an atom can have the same set of quantum numbers. What this means is that if you have two electrons, say helium has 2 electrons, They both want to be in the 1s orbital, meaning they both have an angular momentum, or they both have an L value of 0. One of those electrons can have a plus 1/2 m, and the other will have a minus 1/2 m, meaning that their magnetic fields will cancel. And you actually see that a lot. In a lot of atoms, the magnetic fields, or most of the electrons, their magnetic fields will tend to cancel. This is why, for larger atoms, you tend to see less and less magnetization going on as you get bigger and bigger atoms.